we are going to be talking about mechanics in non-inertial frames. So this comes in useful in handy if you want to talk about what happens on the Earth, for instance. And it actually came up when we were talking about Euler's angles and rotation of rigid bodies. That's chapter 10. I actually used a result from this chapter, even though we hadn't gone through it yet. And it comes up if you want to talk about, for instance, the Coriolis effect, what it feels like if you're on a moving train and you want to relate, because an accelerating train, or if you're riding in an elevator. I also want to preface this with some words about my own experience, because I remember taking upper division classical mechanics with a different textbook. In that textbook, we covered this in the first semester, and I remember ending a lecture where we derived some of the equations we're going to use and thinking, oh my God, what have I gotten myself into? This is so complicated. I came back and taught again out of the same textbook, Fowles and Cassidy, and I went, oh, that's not that complicated. So parts of this can seem really intimidating because there's a lot of hairy, ugly math, and it's not advanced math, it's messy vector algebra. Because we're going to be talking about how you do stuff, how you describe things on the surface of the Earth when the Earth is not actually an inertial reference system. Don't be intimidated by it. Just like when we had the earlier parts where it's long and complicated. Well, it's a lot of equations, but each step is easy. And just keep reminding yourself of that. Each step individually is easy. Okay, so we're going to define, and let me also say why you should care, because you're probably in this class because you're a physics major, and you probably didn't sign up for physics because you thought that classical mechanics sounded super exciting. You signed up for physics because you were fascinated by relativity and quantum mechanics and stuff like that. So you didn't come here to look at hairy, ugly, complicated equations that don't really have any new concepts in them. But if you came here for relativity, you got to get this stuff right before you get relativity right. And that's why you should care, because the formalism that we're going to use, where you talk about relating different reference systems to each other, when we get to relativity, you are going to need that. So if you're barely hanging on by a thread, keep in mind that your goal is something much bigger and much cooler physics. Okay, so we are going to define a couple of reference frames. S naught is our inertial frame, and S is our non-inertial frame. So S is accelerating relative to A. S is accelerating relative to S naught. For example, if this is, if you are standing still and you're watching a car pass by, this can describe the stationary reference frame, and this is the moving reference frame. Or you could have someone riding along on a train and tossing a ball up and down as they ride on the train. And you want to, now obviously if you're on the train, you see someone just tossing the ball, But if you're watching someone do this, you're going to see parabolic motion as the object is tossed. Okay, so then we are going to always use the subscript 0 to indicate the inertial reference frame, and we will use something without a subscript to indicate the non-inertial frame. So M R naught double dot is equal to F. This is Newton's second law. This is in the inertial reference frame. So we will then we will start with an acceleration which is constant. And so here, this is where we're considering the simple cases. We will come back and revisit rotating, but we're not ready to do rotating until we've handled simple linear acceleration, constant linear acceleration. So then we can write that the position well, let's do the velocity. The velocity in the inertial frame is equal to the velocity that you would measure in the non-inertial frame plus the velocity, yes, and the book uses a capital letters for the motion of the coordinate system. So the velocity in the inertial reference frame is equal to the velocity in the non-inertial reference frame plus the velocity of the non-inertial reference frame itself. You can then take the derivative of this, and the acceleration in the inertial frame is equal to the acceleration in the non-inertial frame plus the acceleration of the inertial frame. So again, we're considering only cases where you have constant acceleration, constant linear acceleration, not rotations. So, and this we just did by taking the derivative, and because we're working in Cartesian coordinates, when we take the derivative, we just add dots. We don't have to worry about the changing unit vectors, because this is just a constant. So then we can write that the acceleration in the non-inertial reference frame is equal to the acceleration in the inertial reference frame minus the acceleration of the reference frame. So here we get I'm going to explicitly call this non-inertial. The apparent force in the non-inertial frame is the actual force. Let me put the sub-zero just so it's totally unambiguous. Minus whatever the acceleration is. And times m. So this is often called, that's why I couldn't give this that name. This is often called the non-inertial force because it is the force it looks like you have. So here, if you are in an elevator, inside the elevator, in the reference frame of the elevator, you have no apparent acceleration in the elevator, so you will feel an apparent force that is the acceleration of the elevator. But there is actually a force on you to keep you moving with the elevator. You will perceive it as if there were a force. Well, you would perceive the frame as changing. So I like to ask questions. There's a couple questions that I like to ask on exams. One of them, and some of them are things like, what does the scale actually read? So let's say that you are on an elevator, and to make the math easy, we're going to say that your actual mass is, we'll say the actual mass is 100 kilograms. So here, if you are on a scale, and let's just choose an acceleration of 10 meters per second squared. I like using round numbers. So if you are on the elevator and trying to figure out, and you're weighing yourself on the elevator, of course, if you draw a free body diagram, you have a normal force due to the floor of the elevator. You have your actual weight. There's a few ways that you can do this. So your mass times your acceleration. Now, if you're on a scale, what the scale reads is the normal force. If you do it in the frame of the building, so not moving, you are moving with an acceleration ma, and then this has to be your net force, and this is the normal force minus the weight. These are all scalars in the same direction. Ma equals normal force minus weight. So the normal force, which is what the scale will read, is your weight plus ma. So this would be mg, 980 newtons, plus ma, 1,000 newtons, and the scale would actually read 1,980 newtons instead of your actual weight, 980 newtons. So if you are on an elevator and you are reading if you're standing on a scale on an elevator because you have to accelerate 2, you are going to read a higher weight. Now, you could look at this as well. What is the apparent force? So here, the force, in this case, the apparent force in the frame of the elevator is 0, and the apparent force has to be equal to the force in the reference frame, normal force minus weight, minus ma. And since the weight is a constant, the normal force has to compensate for the non-inertial frame. So one of the questions that I like to write on an exam, hint, hint for my students, is ask you if you're riding on an elevator and it's accelerating with a certain acceleration, and you're standing on a scale, what does the scale read? Now, you can do this without using different reference frames. You should sanity check your result. If the elevator is going up, it takes extra force to get you up, so your weight will be higher because the normal force has to compensate. If the elevator is going down, part of your acceleration to go, you're partially falling, if you want to think about it like that. So what the scale reads will be lower. You can also think about it in terms of reference frames. Your apparent acceleration is 0, but there are a couple of real forces there. Think about it however you want, but you should be able to answer that kind of question. Well, I would say if you're a physics major, but especially if you are in my class. All right, so then I want you to be able to think about what happens if you are riding in a car. So, or you have some sort of cargo in a car. And you can also think about this in terms of accelerating reference systems. So we're going to consider a pickup truck. I actually have a question I like to ask on exams. Part of the reason I like to ask this question on exams is because at one point I drew a really good graphic for this type of problem. So I like reusing the graphic. So you've got something in the bed of a truck, and the truck, there's different variations. It can start at a stop and start accelerating, or it can be going down the road and it stops. I actually like to ask that type of question a little bit more because the signs tend to confuse people. So you have a box or a book or some object in the bed of the truck, and we can consider the case that you can consider either that there is or is not friction. If we draw our free body diagram, we have a normal force, we have gravity, and then we have friction. Let's assume that this is accelerating, actually this would be decelerating because the friction we'll call it a book. The friction has to lead to a net acceleration in this direction. That tells you that the friction has to be in the same direction as the acceleration of the truck. So we can do net force in the y direction is n minus w, which is 0. So n equals w. The magnitude of friction is mu sub s. If we have, mu, let's leave it at mu, and it could either be kinetic friction or it could be static friction. And this is always the maximum. So this is mu mg. And so then if you have, if the truck is, let's say that the truck is accelerating at, round numbers, 100 meters per second squared. No, that's really fast. That's too fast. 10 meters per second squared. Here, as you can probably tell, I'm doing my favorite thing. I'm flying without a net. I have in my note margin this type of example without actually writing down in detail what the example is. So here is, we're going to leave off the vectors because we're talking, we're talking entirely in the x direction. So this has to be an acceleration of negative 10 meters per second because I've already decided we're going that the friction is in that direction. So the truck is slowing down with an acceleration of 10 meters per second. Let's make the book no, we won't make it 10 kilograms. That's a very heavy book. It's a big fat analog dictionary. Every one of you should have one of those, even physics majors. You should always have a dictionary. You should always have analog too. They're better than the online ones. All right, so 10 kilograms. And so our weight is going to be 98 newtons. Let us do we will do a kinetic friction. We'll do 0.1. Mu sub k is 0.1. And I'm going to say, well, what is the acceleration of the book in the truck? So that means that friction is 9, and the way that I have written it, it's in the negative x hat direction. I'm going to use coordinates with this x hat and this y hat. So friction then has to be mu sub k times the weight, negative 9.8 newtons. So what is the acceleration of the book inside of the truck? It is the actual force, which is negative 9.8 newtons minus minus 10 kilograms times negative 10 meters per second squared. So the actual acceleration, the apparent acceleration in the inside of the truck is 90.2 newtons. So if you are sitting in the truck, let's see, did I get the sign correct? The actual force is in the negative x hat direction, and that means, so here the truck is slowing down. Inside the bed of the truck, it looks like the book is going forward with an acceleration of 90.2 newtons. So the things that trip people up here are that they went and like a third to half of all classes, even when I ask this in an upper division class, people put some extra force in there. No. Every force that you draw on a free body diagram has to have some place it comes from. So you don't have anything, just stick with your free body diagram and trust it. These are the only three forces that you have. Now check your math, but think it through. I don't know if you saw, I had to think this through and then remember, oh yeah, the truck is slowing down, so it does look like the book is sliding forward. In the reference frame of the truck, that book is going, woo! If you had higher friction, the book would go forward slower. Now, if you're standing there on the ground, the only force that you see is the force due to friction. So what you see is that the book had started at a relatively high velocity. It's slowing down, but it's not slowing down as fast as the truck. So we're going to consider a pendulum. It says, example 9.1 says pendulum in an accelerating car, because everybody keeps a pendulum in their cars. I'm going to make a train. We like trains in my family, so it's actually going to be a train. let us specifically put it in the caboose. It's a tender. And here is the steam train. Oof. Come on, we can do better than that. Let's make it like this. This is, why am I, no, of course, the smoke goes backwards. I should know that. Here's our coal. We got a steam dome and a sand dome. We're going to make it a big boy locomotive, Union Pacific big boy. And back to physics, we got a pendulum in our train. So this pendulum is at an angle of phi in the train. And we want to know what the effective acceleration is. So here we're going to write x, y. We will make our acceleration. We'll leave it general first, but we're going to put it, of course, the acceleration is entirely in the x direction. So we'll do a equals a x hat, and then the force, the actual force is the tension minus mg and this is an F0. So the apparent force is the actual force minus the acceleration. So this tells us, we want to know in the frame of the train, the net acceleration is 0 because the pendulum is at some sort of equilibrium. It's not rocking back and forth. So the net force is 0, and then we can ask, what is the tension in the string? So we have the tension, and this we can write tension minus mg y hat. So the tension minus mg y hat plus at a x hat is equal to 0. So we can get that the tension is mg y hat minus the acceleration x hat. You can also write this as mg effective, as if there is some sort of effective acceleration there. And then you could, so this effective acceleration, you can figure out that angle phi, tan phi is a over g. Here I have a, I should have put it as ma. The reason I know that is because my units work out incorrectly. And then here, if I want to write this as an mg effective, then my m's get factored out. Okay. So here, these are the relatively straightforward cases, but of course we're going to tackle some of the more complicated cases. So then we can turn to the question of what happens with the tides. So when we have the tides, here's Earth. The water, because water is deformable, and here this is drawn to exaggerate it, the effect, the water that is closer to the moon, and so far there is an effect on the tides due to the sun, but we're not going to talk about it yet. The water on the side closer to the moon is more attracted to the moon, but you actually see two bulges because the water on the opposite side of the moon experiences a significantly lower force due to the moon than even the center of the Earth. So it gives you the apparent effect of having this stuff pushed out and that stuff pushed out, but what's really going on is that this side is less attracted to the moon than the stuff on this side or than the center of the Earth. And we have to consider this effect numerically, we have to treat this carefully. So here I have drawn figure 9.3. And I tried to draw it large enough that you can actually see details. And we're going to try to calculate the effect of the tides. So here we've got the distance between the center of the moon and the center of the Earth. And we are going to look at a slight, we're going to calculate the effect, the difference between the force on the Earth due to the moon and the force or the acceleration on the Earth due to the moon, and compare that compare the acceleration of the center of the Earth due to the center of the moon, and compare that to the acceleration due to the moon when you are not quite at the center. So this d0 is the distance between the centers. D is the distance between the center of the moon, because we're looking at the impact of the moon, and this tiny bit of chunk of mass m. And r is the vector between the center of the Earth and the position of that mass of the moon. So the acceleration due to the center of the Earth the acceleration of the Earth's center due to the moon. I'm not sure I like the notation, but I'm going to stick with it to follow the book. So the force goes like gmm over r squared. So now the acceleration of the center is written like that. The apparent acceleration when you are on the surface of the Earth is equal to the actual of the Earth. And then this is, for this chunk, mg minus this d0 naught hat is just a unit vector in the direction of d0 in the direction of d0. And then there could be some forces, some non-gravitational forces, and then we have the force, the actual force here, G M M. I dropped there should be an extra M there. Big M, little m, and then here we have the, let's see, this actually should not have the d naught. And so all of this is our actual F. And this is the acceleration of the coordinate system. So this is A. And then this is equal to the apparent force of the tides plus mg plus whatever non-gravitational forces there are. So we are left with, let me actually migrate it over here, the force of the tides is, oh, and then minus A. So just, this is, I like to make sure that what I write on the board is actually true. So then we can read by comparison between these two equations. We can read off, here, I don't actually want the A. The force of the tides is then this, the difference between these two forces. So the force of the tide is negative GMM, mass of the moon, mass of whatever thing we're testing, d hat over d squared minus d naught hat over d naught squared. And if we look at what is actually going on with the force, when d is less than d naught, so when you're on this side, then this term dominates at the top, and the components cancel, and the top components cancel the down components, and vice versa. So here and here, you don't have any net force, but when this length is less than that length, you have a net force which is in that direction, and the opposite is true on the other side. So there's some more argumentation in the book, but I'm not gonna go through it because I find it, like, you can work your way through it, but it's a little convoluted. And what we're gonna do, so basically you don't have to worry about the non-gravitational forces, which include things like the buoyant force. And we're mainly going to focus on the effect from the tide. Now we can look at this. It is hard to work with, it's hard to work with a vector equation, but since this has the same form of a gravitational potential, then what we can do is we can actually write this as, so this has the same form as a gravitational force. So what we can do is that we can actually write this as a potential. We can write an effective potential from the tides. And when we do that, what we're going to do is this form. We just integrate. So this has the same form as if we had a gravitational force. So we have negative GMM over, in this case, let me actually do what the book did and factor out those constants. Negative GMM, and then 1 over d. So when we integrate f dot dx, we get a 1 over d here, and then here we get an x over d naught squared. So here the d naught is a constant. This x position, we follow the book's notation, x, y. We're going to go into the, so we're only integrating along the x position. So then we're going from here to that position there, which has the position x. Okay. So then, so we're integrating along the d direction here, integrating along the d naught direction. And then we're going to work with this. And this part gets, here's where I'm going to draw a big equation, and we're going to write, I'm going to draw a big figure, and we're going to write everything in terms of its parts. Bear with me here. All right, so if we write these in terms of coordinates, and this is at negative x, y, so we can write our vector r equals negative x, x hat plus y, y hat, d naught equals d naught x hat, d equals d naught plus r, which is d naught minus x, x hat plus y, y hat. And here I'm going to use d naught hat is just x hat. Now that we have d, we can get d hat, because d hat is d divided by its magnitude. So d hat is this over d naught minus x squared plus y squared, and the square root of all of that. And then we can write the potential u sub d is negative GMM over D. And we can get so that's just integrating from there. This is how you get this term. To get this term, we take our force term just from the D0 part. And we integrate. When we integrate, we're going from here to here, and that's where the x term here comes from. All right, and then we are going to compare the potentials in different regions. So we are going to compare, so this is point P, this is point Q, and this is point R. So we're really interested in what happens at the top. which is equivalent to what happens at the bottom. And when we want to look at what happens on the moon side compared to the side on from the opposite side of the moon. So the potential here, if we're looking at actually I wanted to make this on the surface of the water. So when you have a deformable fluid, they're going to have an equipotential surface everywhere because the fluid is going to deform until there is no net force on it. So the potential here on at the edge of the water is the same as the potential on the surface of the water is the same as the potential on the surface of the water when you're at point Q. And I should mention, we're assuming right now that the entire Earth is covered with water. Of course it is not, and there are slight corrections. And then if you compare just the potential due to Earth's gravity here, where you are on the surface of the Earth, versus here, where you have some net displacement, then you are further from the Earth there. So you have a potential difference of mgh just due to gravity, and that has to equal the tidal force. Now, when we consider radii close to the radius of the Earth, and then we will consider where we are roughly along the equator, roughly perpendicular to above the pole, there. This potential is negative gm m over d naught squared plus re squared square root. And this thing is just d. And the reason for that is that this x is 0, so we're only left with that term. Now, we will do what all good physicists do and take a Taylor series. And I can write this then as 1 over 1 plus re over d naught, quantity squared, square root. And the Taylor series of this, the first two terms are 1 minus 1/2 re over d naught quantity squared. So the effect of the size of the tide at point, let me actually squeeze that in over here. The size of the tide at point Q is roughly negative gm m over d naught, 1 minus 1/2 re over d naught quantity squared. And then we are going to, let me actually here just a refresher on Taylor series. If we have f of x equals 1 over 1 minus x. Let's see, did I do the square root of 1 minus x, and then you do f prime of x, this is equal to negative 1 minus x to the negative 1/2. So at 0, this is 1. At 0, this is also 1. Oh, that's rolling off of the board. So when we take the Taylor series, this is 1 minus, oh sorry, this is negative 1. 1 minus negative 1 times x to minus x, and then times 1/2. I dropped my 1/2 here. Then we're going to come back and look at the potential here. All right, so then we are going to look at the potential at point P. This is negative g m 1 over d plus x over d naught squared. This one's a little trickier. So negative g m over d naught. So I'm pulling a d naught out of there. So I have d naught over d plus x over d naught. Now I have written this in terms of numbers which are unitless. I like writing things in terms of numbers which are unitless because it's a little harder to make stupid mistakes, and I love making it harder to make stupid mistakes. Now I'm going to go back to what is d. D is, so d over d naught. My d is d naught over x hat plus y hat. So now the magnitude of d over d naught this I can write u of p then as negative gm over d naught 1 over 1 minus re over d minus re over d naught. Let's see, this should be d naught. So this is, so d is d0 minus, d is re minus d0. So here, this is this term, this is this term. And now here, this is approximately 1 plus re over d naught plus re over d naught quantity squared. So here I have taken the second term in the Taylor series. And so I am left with this term gets canceled out by that term, and I am left with the potential at point P is negative gm m. I've got the little m to indicate this is the moon, times 1 plus re over d naught quantity squared. And then I want to look at the difference between these two. So I'm going to sketch this over here. It's getting near the end of the day, so I'm rushing a little bit. All right, so we're going to take the difference and take advantage of the fact that we know that this has a potential difference due to gravity alone of mgh. So we will use u from the Earth at point P minus u from the Earth at point Q is equal to mgh. We're going to use these two forms, and taking a deep breath because it's a lot. So we get negative gm over d naught 1 plus this term minus 1 plus 1/2 RE over D naught quantity squared equals mgh. The question is, what is that h? We'll simplify this. So this cancels out, that cancels out. We are left with negative 1/2 GMM over D naught RE over D naught quantity squared equals M, and then G, little g, is G times the mass of the Earth over RE quantity squared H. So now, this is the mass of the moon, that's the mass of the Earth, and this is why we kept that subscript the entire way through. We have M's on both sides. We have capital G's on both sides. And we need to move these we're going to move these R's here, and we're going to move that M there. We get H equals, and here, actually these have the same sign, so this should be a 3. I made that mistake. That's why I should have notes, and you know I like to work without a net, but this time I have a net. So this is negative 3/2 the mass of the moon divided by the mass of the Earth. And then we have RE to the 4th. That's because this gives me 1, 2, 3, 4 divided by D naught and then cubed because I got 1, 2, 3. And this works out to be 54 centimeters. Those are the tides due to the moon. You can actually change the mass here and consider so this is the height due to the moon, the height due to the sun, same thing, but this mass is now the mass of the sun instead of the mass of the Earth. And this is now the distance. This D naught is the distance to the sun. The radius of the Earth came from how far are you from the center of the Earth. You're looking at the difference in the net force on the surface of the Earth. So this stays the same, but this changes because this is the This is now the Sun-Earth distance, and this works out to be 25 centimeters. So roughly, you can ask, because the tide from the Earth and the tide from the Moon and the tide from the Sun can be working together and add up, or working against each other and counteract, so you can get ranges of tides from about 29 to 79 centimeters. And of course, you can have other effects like the impact of the land masses and slight changes in, the effects of other bodies, but this is a pretty good approximation. So we're going to be talking about how we describe a body which is rotating, and what we're going to actually build up some rather complicated mathematical formulas to describe ultimately things like the movement of something on the surface of the Earth, even as the Earth is itself rotating. So we're going to start a little more general and pin it down as we go on. So pay attention to where we're working with something general and where we are getting to a very specific case. So we are going to describe a couple of cases of rotating axes fixed on a rigid body. So there's one case where you can fix the axis to the body, and another where you have no fixed point. So you have, say, a gyroscope that is touching some surface and it stays on that surface at a point, or you can have, say, a rugby ball flying through the air. And we are going to talk about the motion of the center of mass and describe the motion relative to the center of mass as well. And we're going to use, everything's named after Euler in math and physics, because he came up with a lot of this. We're going to use Euler's theorem in this case. That means that a rotating body you can describe a rotating body where there's a single fixed point in terms of some rotation about some axis through that fixed point. We call that point the origin. And we're going to describe the angular velocity. In much of this chapter, we're going to be working in cases where the angular velocity is constant. So the angular velocity is the rate of change of the angle. And we're going to want to describe this as a vector. And I'm going to be a little lazy as I record this because you guys are seeing the mirror image. So when I don't have to do a lot of cross products, I'm going to be working with my left hand, not my right hand, rather than worrying about the mirroring. So then we're going to describe, we will use a vector notation for the angular velocity. And so the angular velocity written as a vector is, and we want to write the angular velocity as a vector because as an analog to velocity is a vector, angular velocity should be a vector too. And so we're going to write it in terms of some unit vector. And then the question is, what is that? So if I have something which is rotating, let me make a big marker chain so that you guys can see something. Actually, let me use a white marker instead. That will show up a little bit better for you. So I have something which is rotating. When I have it rotating, what I'm going to do is I'm going to take my right hand and I am going to curl my fingers in the direction of the rotation, and then my thumb points in the direction of the angular velocity vector. So here you can see it. If I do it this way, you'll see it a little better. So I'm going to curl my fingers in the direction of the angular velocity, and my thumb points curl my fingers so that it's moving with the rotation, and my thumb points in the direction of the angular velocity. And that is the convention so that we get the directions we want, because we want the torque to be I omega, which is R cross F. This is the force creating the rotation. This is the moment arm between the axis of rotation and where the force is applied. Um, sorry, this is not I omega, this is I alpha. And I alpha is d omega dt. And this also happens to be just like the force is, so torque is the rotational analog of force. So so force is the time rate of change of the momentum. The torque is the time rate of change of the angular momentum. And omega can be time dependent, but there are many useful applications, for instance, the rotation of the Earth, where omega is actually a constant. So then we're going to derive a useful relationship that we're actually going to use over and over again in this chapter. So we're going to try to describe the relationship between a vector and the velocity of a point at that. The vector, so the velocity due to rotation, and then the derivatives of vectors and of unit vectors at different locations. So let's start with drawing the system. That is not a straight line. So this is, I'm trying to draw figure 9.7. So here we have the angular velocity, and we're going to make this, it is clockwise in my frame, so you see counterclockwise because you see the mirror image. So that shows the rotation. The object is rotating like this. So our angular velocity vector is like this. We have some point, we have so this is our origin that we're using, and we have something at point P. So here, this is the vector r between the origin and point P. And this is if P is rotating with angular velocity r, it sweeps out a circle. That is not a great circle, but it is a good enough circle. There is an angle theta here. And so here we're imagining, think for instance of a spot on the Earth's surface. So we're looking at a point P, and this is relative to the center of the Earth. Although the math is more general, so this is the angle, theta then would be the angle from the North Pole. That is called colatitude, not latitude, because the latitude is the angle from the equator. So this is the angle from the North Pole. And then we want to know what the velocity of the, due to the rotation is. So it turns out that the velocity due to the rotation is the cross product between omega and r. So the cross product is going to have a magnitude of the product of the two magnitudes and then sine theta. So if we look at what this distance here is, the distance between the axis of rotation and the distance between the axis of rotation and point P, let me switch colors so that we can see that. This is r sine theta. So that's that distance there. And then, so that has so if you wanted to look at the the velocity due to, at this point P, due to that rotation, the velocity is the radius times the angular velocity. So the radius, the distance from the axis in this case, is r sine theta, and then multiplied by the angular velocity gives us the velocity at this point P due to the rotation. And then we can look at, we want to ask about the time derivative of an arbitrary vector. So this is telling us that the time derivative of r is equal to omega cross r. And then it turns out that if we want to know the time derivative of any vector due to rotation, so you've got, let's say that you're looking at the distance between the displacement between Knoxville and Nashville as the Earth rotates, the time derivative in the stationary frame for that distance is going to have the same form. The time derivative of that vector is omega cross r, or sorry, omega cross e for any vector, e. And then we can look at the, so we can ask what happens if we have multiple angular velocities. So let's say that you have a merry-go-round on the surface of the Earth, and you want to talk about the motion of that merry-go-round relative to a stationary frame. You probably don't really care about a merry-go-round, but you might care about a hurricane. So we know that the velocities add. So if you have, let's put another point Q up here, and we want to look at the vector between P and Q. And we want to say, so if we want to add velocities, velocities add. So if we want to know the velocity between points 1 and 3, that is the same thing as the velocity between point 3 and 2 plus the velocity between point 2 and 1. And this actually means that the angular velocities add too, because here I can write that the velocity between points 3 and the angular velocity between 3 and 2 is the omega between 3 and 2 crossed with r. And let me switch this to a 2. Plus omega between 2 and 1 crossed with r. And this has got to be equal to omega 3, 1 crossed with r. So here I have omega 3, 1 crossed with r equals omega 3, 2 plus omega 2, 1 crossed with r. So omega 3, 1 equals omega 3, 2 plus omega 2, 1. So our linear velocities add, our angular velocities add when we write them as vectors. And we will use some notation following the book. We will use a lowercase omega for the velocity of a body, the body of primary interest. So if we're talking about a ball or a bullet or a tomato on the surface of the Earth, that we call lowercase omega. When we are talking about the angular velocity of the non-inertial frame, we're going to use a capital omega. So that's the velocity of the non-inertial frame itself. And lowercase omega is often unknown, while uppercase omega is often known. So then what we're really interested in is time derivatives in a rotating frame, because we want to take things on the Earth and be able to start talking about things on the Earth moving, taking into consideration the fact and how they apparently accelerate, even though there's not actually forces. because we're using a non-inertial reference frame. So we're doing this in general, but the most important rotating frame for this chapter, and frankly for most applications of human interest, is the Earth. So the rotation of the Earth, we go through 2 pi radians in 24 hours. And there's 3,600 seconds per hour. And this works out to be 7.3 times 10 to the negative third radians per second. So this is small, but it is sometimes measurable. And now a little aside. What we're trying to do is develop mathematical terminology so that you can describe physical situations. We have thus far, in a lot of cases, treated the Earth as if it were an inertial reference system. The way that we solve problems as physicists is that we start with a simple problem, and we solve sometimes we're solving the problem that we can solve as opposed to the problem that we have. And we try to solve problems that are an approximation of the problem that we have. And then we're going to successively add more and more complications, always going back and checking that we get something reasonable in limiting cases. So if you're talking about the motion of a basketball flying through the air, mostly you can ignore the Earth's rotation, and then we can go back and calculate the size of the effects due to the Earth's rotation and see if that is still consistent with what we observe. So sometimes we can ignore this. What we're going to learn how to do also is calculate when you can ignore it and when you have to take it into account. So the 2 frames that we're talking about have a common origin. We have something fixed to, let's say, the center of our galaxy, although it's not entirely obvious. Whether you should, what you should do, what your stationary frame is, and then we have a frame which is rotating with the Earth. So that stationary frame is going to be S naught. This is inertial, but it's inconvenient because I don't know how to measure things relative to the center of the galaxy because I am on Earth. So we will measure things, we can measure things in terms of the surface of the Earth. So this is, but we can't measure things relative to the galaxy. This makes it really easy to calculate because it's inertial, but it's also really inconvenient. And then we have S, which is fixed to the Earth. This is non-inertial because the Earth is not an inertial reference frame, but this is convenient because this happens to be what we actually measure. The notation in this chapter gets a little bit dicey because I have to be very careful about distinguishing when we're talking about the inertial reference frame and when we're talking about the non-inertial reference frame. And we're going to derive the math in general, but if you need a concrete picture in your head, and that often helps, think about the Earth and think about the Earth as an example. So then we've got our rotating frame, where we will often fix z to be the direction of omega, but at least in principle they don't have to be the same. So you've got your inertial frame. Actually, I'm flipping back to the notation that I learned from, which was Foucault and Cassidy, which uses primes. This book uses uses zeros and non-zeros. So in that vein, this is z0, that's x0, and z and x are changed from that. And then we're going to look at a time derivative of an arbitrary vector in that frame. So whatever reference frame we're working in, and this is drawing on a little bit of linear algebra. Not everybody has had linear algebra. So take it on faith if you have not had linear algebra yet. I want to relate the time derivative of some arbitrary vector q in the frame S naught to the time derivative of the vector q in the frame S. So this is in the inertial frame. So if I, for instance, am talking about the velocity, which is an example of the vector q, then the velocity, I want to relate the velocity in the inertial frame to what I actually see in Earth, because I'm going to see something slightly different in Earth. I can always write vector q in terms of basis vectors. You've actually done this before, but we didn't use this terminology. So I can write the vector q in terms of basis vectors. So for 3 dimensions, I have 3 basis vectors. You guys are used to this, where this is x hat, y hat, and z hat. This is saying I can decompose a vector into its 3 components. But I'm going to write it with some notation just to make life, well, it will in the short term make life harder. In the long term, it's going to make life easier. All right, and I can do this in any basis. So I am going to use, and I'm slightly deviating from the book's notation here because I like being a little more explicit. The book uses 0 and then it's implicitly, I found it confusing. So here, this would be, for instance, this is in the inertial frame. So you have an x hat, y hat, and z hat fixed to the inertial frame, and then you can fix them relative to the Earth, where you might pick any general origin. And if you fix them, say, to this particular point here, this is x hat, this is y hat, and this is z hat, then as the Earth rotates, my x hat, y hat, and z hat are going to rotate too, because I've decided to fix them to me. I am the center of the universe, and that means that they are actually changing with time, because I'm not really the center of the universe. Even if I think I am. And now we're going to look at the time derivatives. So these basis vectors are actually constant because the inertial frame is constant. Now, just an aside, I'm talking about this as if it is x hat, y hat, and z hat. Those are not special vectors. We can always use different vectors. So you could use any basis you want, but when you're fixing them to the inertial reference frame, they're constant, whereas these guys are not. So we're going to do the time derivative, and this side is relatively easy. So dq dt. This part we have to apply the product rule. So here, this is this side. If I do this in the S naught frame, I look at this side, and here I have I equals 1 to 3 dqi 0 dt. And now these are just constants. Now they happen to be constants which are vectors, but they are just constants. So this is just how we would express the derivative of q in the S naught frame. Then we look at here at this. Now here, this and that can both change. So we have to write this as the sum. And here I'm a little more explicit in my notes than I was actually, or sorry, I'm a little more explicit here than I was in my notes because I think it's probably helpful. So we have that. Then we have this time derivative here, except that what we talked about in the last section was that the time derivative, so in the last section we said dE dt in the rotating frame is omega cross E. Now that is going to be true as well for these vectors right there. So I can say dE hat I dt is equal to, in this case I'm talking about the rotating Earth or the rotating body, capital Omega cross E hat I. So then I can come back to this equation, and this term is replaced by omega cross, let's see, this term is replaced by omega cross E hat I. And these guys are just, so I'm going to write this in a few more explicit steps. I have my sum, let's see, here. This term is just, this term just is the apparent dq t in the S frame, where I just want to be a little bit more explicit. So I have dq dt in the inertial frame is equal to dq dt in the non-inertial frame plus, here I can pull the omega out, and I have capital Omega crossed, I can pull it out of the sum because it is itself a constant. So crossed with the sum over I of qi E hat I. So this is, actually I'm going to write this up here because this is an interesting result. And well, I'll squeeze it in here. All right, actually, how should I write this? I will go ahead and replace this. This is simply Q. So I can replace this by Q. So I want you to think about this. At this point in your studies, at least if you had me for your previous classes, and most of you did not, you have at least been introduced to the concept of an operator. And I want you to think of this as so an operator is like a derivative operator. It acts on something. The operator d dt acts on something and means that you take the time derivative of that. So we're going to write this as the operator d dt in the inertial frame is equal to d dt in the non-inertial frame plus omega times the cross product. So when it acts, it has to act on a vector, and then you basically replace, for an arbitrary vector, you just have these operators act on each vector. Thinking of it as an operator is going to help when we get to taking a second derivative, where we're going to use this operator twice. So since we're going to use this, we're going to tuck it somewhere useful so that we can keep going with our derivations. So I've written this equation up here, and now we're going to use this. We're going to apply it twice, because what we're trying to get, we know the force. We know how to figure out what the actual forces are, because you guys are now in second semester upper division classical mechanics for physics majors. So you're pretty good at free body diagrams. You can figure out all the forces. But that is only in an inertial reference frame. So we want to relate that, the force in an inertial reference frame, to the apparent acceleration in the non-inertial frame. So that is, now this is Newton's second law. The second derivative of the position vector with respect to time times mass equals the force. But this is only valid in an inertial reference frame. So we're going to try to find out how to connect it when you are looking at something which is not in an inertial reference frame. Let me do a little bit of an aside. A few decades ago, when I took my upper division classical mechanics class, I looked at this result that we're about to derive and wondered what on earth I had gotten myself into. It was weird, it was complicated, it was convoluted. After teaching upper division classical mechanics this is my 4th time teaching this material, I get it, and it looks really easy. I do not expect you to get it instinctively the first time. When you see this, you're going to have to go through everything slowly and carefully and methodically, and it's all good. I hope you can follow each individual step, and then when we get the result, I want you to be able to apply the result pretty well with some guardrails, getting a little bit of help from your instructor, but it's not going to be second nature just yet. And that's okay. Okay, so now we are going to attack this problem. We are going to start, so think of this as like an operator. So I have drawn Q in a different color. We're going to apply the operator twice. We're going to start by applying it once. dr dt in the inertial reference frame is equal to dr dt in the non-inertial reference frame plus omega cross r. And let me just, for good measure, call this in, let's see, this is, yes, this will be r regardless. We can write r. We can write r in terms of the basis vectors in the inertial reference frame or in terms of the basis vectors in the non-inertial frame. That's really just a choice. How are you writing r? But when you do this time derivative, that's when it matters. Now we're going to apply this operator. So d squared r dt squared in the inertial reference frame is this operator acting on this dr dt in the non-inertial frame plus omega cross r. This is going to give us d squared r dt squared, so written in the non-inertial reference frame. Then we get omega crossed with dr dt in the non-inertial reference frame. And then we get this time derivative acting on this term. This is a constant. If we're talking about the rotation of the Earth, the speed of the Earth does not, rotating around its axis does not change. So the derivative operator moves through this, and we get a term, omega cross dr dt in the non-inertial frame. And then here we get, let me see, I have until here. So this screen goes a little bit further than you guys can see, but it doesn't do me any good if you can't see it. So omega cross omega, I haven't drawn the cross. Omega cross omega cross r. Okay. Now we are going to do a little bit of simplification. We are going to reserve the dot notation for when we are in the non-inertial reference frame. So here, I'm just going to note here that this is the force divided by the mass. I'm going to multiply through by the mass later, but let me just pin that down. I'm going to write this as force divided by the mass. And you can figure out, so if you do a free body diagram in the Earth's reference frame, that's also telling you the forces in the, that's also telling you the forces in the inertial reference frame. All right, here, allowing us to rename things that are in the non-inertial frame with the dot notation, this becomes r double dot. This becomes r dot. This becomes r dot. So I have F over M equals R double dot plus omega cross R dot, and then actually these two terms are equal, so I can combine them. I have a 2 omega cross R dot, and then I have an omega cross R. And I'm going to rearrange, I'm going to actually do one trick. I'm going to flip the order here, so I have a minus sign in the second two terms. So I have R double dot minus 2 R dot cross omega minus, here I am going to, so I flip this, I get omega cross R cross omega. And I'm going to move all of this onto that side and multiply through by m. So I get m r double dot equals the force plus 2 r dot cross omega plus omega cross r cross omega. Okay, so this is telling me that my apparent force in the non-inertial reference frame is equal to the actual force plus this term, which we will call the Coriolis force, and this term, which is the centrifugal force. So, then what we're going to do, we're going to look at these separately. So first of all, I want to pause and give you, this is intimidating and scary, and that's okay. You don't have to be cool with this. This is a big, ugly equation. Let me also say you could do this in a slightly different way, where instead of writing this as an operator in the inertial reference frame, you write it as an operator in the non-inertial reference frame, and then you get the signs to work out the way you get the signs to work out right without having to switch the order of the cross products. Or you switch the order of the cross products earlier on. So how you do that is write this operator as ddt in the non-inertial frame is equal to ddt in the inertial frame minus omega cross the vector. And still, if you want everything to have positive signs, then you would have to rearrange the vectors a little bit. So we're going to pull these out and talk about each of the terms separately. And you've surely heard these terms before. There actually is a quote that normally I don't think that it is worth quoting the book verbatim, but I think that it is in this case. Okay, so the Coriolis force is then 2r dot cross omega, and the centrifugal force, and here the textbook's abbreviation is not so awful, so we'll just use it, is omega cross r cross omega. So this one only depends on velocity. So if you have something at rest, you don't have any apparent centrifugal force. This one depends on omega squared, and we had a very small omega, so omega for the Earth is 7.3 times 10 to the negative. I can't read my handwriting. Is that 10 to the negative 5 or 10 to the negative 3? So 10 to the negative 5. So when you get an omega squared term, you have 10 to the negative 10 in SI units out in front. So here, to get the Coriolis effect to matter, you have to deal with, to get the centrifugal effect to matter, you have to have things that are either acting over long distances or long times, so that this is large enough. Whereas the Coriolis effect requires you to have things acting on, they have to be moving quickly or long time, or you have to be very sensitive because you're doing a very precise measurement. And here I'm actually, this is from a few sections later, but it, I think, is worth quoting verbatim. Both the Coriolis and the centrifugal forces are at root kinematic effects. That is, that they result from, they are kinematic effects resulting from an insistence on using a rotating frame of reference. That is, the Coriolis force and the centrifugal force come up because we're using the Earth as a frame of reference as opposed to using an inertial frame of reference. So I like that way of thinking about it, and this is why physicists often grumble and talk and complain when people talk about the Coriolis effect or the centrifugal force, as we say that they are not real forces, because they aren't caused by any action. They are simply because we are using a non-inertial reference frame. So then what we can do is that we can look at the relative sizes of the Coriolis and the centrifugal force and decide when we have to worry about each. They are vector quantities, and that vector aspect does matter and does matter a lot, but we can look at what the maximum values are. So the maximum value of the Coriolis force is mv capital omega, where this is the rotation of the Earth. This, by the way, we're moving into talking specifically about the Earth. The equations that we derived in the last section are applicable to any rotating system. So you could be talking about things on the surface of the sun, or the rotation of the Milky Way, or the rotation of a ball. It doesn't matter. But here we're talking specifically about the rotation of the Earth. The centrifugal force, then the maximum goes, let me just put max. The maximum goes like mr omega squared. So then we can look at the ratio. The ratio of the Coriolis to the centrifugal, max, is the, so let me be a little more explicit. We can write this mv omega over mr omega squared, and 1 omega cancels, the m's cancel, and we are left with, those are actually different colored markers even if they don't look like it, the velocity of the object divided by r omega. Now, this is just the velocity of a point on the equator. So the velocity of the object divided by the velocity of a point on the equator. This velocity of a point on the equator is about, the book cites 1,000 miles per hour. In a physics textbook, who do we think we are? Engineers? No. So better units, 1,670 kilometers per hour, but our beloved SI works out to be 460 meters per second. So here, you are dominated by the Coriolis effect when your velocity is larger than about 460 meters per second. Way faster than cars, but you can get, for instance, ammunition that does get to go comparable speeds. Now, here I have to mention, like, all of these equations were initially derived because people were interested in making better weapons and firing things accurately over long distances. So even if you're a pacifist, I'm sorry, physics has a lot of these examples that involve bullets, because that's what the equations were derived for initially. So you can frequently ignore the Coriolis effect for low speeds, and then we can look at what happens with the centrifugal effect. Now, low speeds, but also when you don't need to be super accurate, because the Coriolis effect can still matter. And as we'll talk about, the Coriolis effect causes a deflection, whereas the centrifugal effect mainly affects the magnitude of the acceleration. So here, if we want to talk about the centrifugal force explicitly, here we have the origin. This is omega, our rotation. We have some point, P, that we are looking at. It has a position vector, R. And we have this distance, rho. The distance from the axis of rotation. And then, so our Coriolis effect, or sorry, our centrifugal effect is omega cross R. So omega cross R is towards me. Here I'm working with my left hand because of the mirror image. And then we have crossed with omega. So I have this vector crossed with omega. And I'm going to switch colors again. This is only slightly different, but it's the best that I can do. So that is omega cross R cross omega. And here I've drawn this so that it is, so that R and omega are in the plane of the board. And then omega cross R is towards me. And what you see is that the centrifugal acceleration is always, this sort of makes sense. It's the apparent acceleration because this point is rotating like this due to the rotation of the Earth. And so then we can write this as that force, the magnitude of the centrifugal force, is m capital omega squared rho hat. So rho is always perpendicular from perpendicular to the axis of rotation. So it's sweeping out as you rotate like this, it's rotating. So it's always pointing out from the center of the Earth. And we actually can further say that rho is is in this case the radius of the Earth times sine of theta, not the latitude, but the colatitude. And so what it means is that if you are on the surface of the Earth, you feel an apparent force pushing you, let's say pushing you off the Earth. So then if we talk about free fall acceleration, so you've got something falling. And we can draw that picture. This is figure 9.10. So I've got something falling. This is omega, the rotation of the Earth. And that is just a little bit taller than I can fit. Capital omega is like that. And I have some point here. And this is, so the Earth is spinning in and out of the board. This is theta. And the true force of gravity is directly towards the center. And we call this mg naught. But you also have this Coriolis effect, which acts like this. And we can further, if you know, for good measure, we can write the force, the true force of gravity is negative gmm over r squared r hat. It's always pointing towards the center. Our origin is the center of the Earth. And we'll write that mg r naught. But of course, the effective force is the force due to gravity plus this Coriolis. So mg plus m r omega squared sine theta rho hat, where here I have used rho equals r sine theta. So in general, the acceleration is not in fact just the acceleration due to gravity, but we have this tiny perturbation, which is a vector perturbation, so it's changing the direction and the magnitude of gravity due to the rotation of the Earth. Now, in practice, because omega is 7.3 times 10 to the negative fifth hertz, and r is 6.4 times 10 to the sixth meters, omega squared r is 0.034 meters per second squared. So this term here is small because we should compare to g equals 9.8 meters per second squared. So the effective, so when you are at the, and then here, if you want to really look at the difference, you, if you want to write this vector for gravity, this is mg naught r hat. And here I have to decompose my rho hat into an r hat component and a theta hat, or sorry, an r hat component and a theta hat component. So where theta hat is the increase, so if I draw my unit vectors, r hat is here. The unit vector by convention is in the direction of the increasing variable. And my theta hat then is going to be like this, because as theta increases, it's the direction of increasing theta. So now I want to write rho hat in terms of r hat and theta hat. So rho hat makes similar triangles. Rho hat is, I'm going to double check this. Yeah, so it is sine theta r hat, and actually here I should note this is in the negative r hat direction. I messed up a sign there. So rho hat is sine theta r hat, and it is positive plus cosine theta theta hat. So here, this is going to be, write this, let me collect terms. M G naught. It's a negative mg naught minus r omega squared sine squared theta, because I'm plugging in this expression for rho hat in the r hat direction, and then plus mr theta squared cosine theta sine theta in the theta hat direction. And this is where I think that the book was a little bit less explicit than it could have been. And then you want to compare the magnitude of this term, r omega. So we'll take the maximum of this term. First of all, this is actually maximum at 45 degrees. So when you are about here, because you have the squared term, you have a 0 at the pole and a 0 at the equator. Sorry, no. You have a 0 here, you have a 0 there. And at the equator, this is the maximum change from G. So we want to look at the maximum change from G. And this works out to be about 0.3%. So there's a difference between the effect of G at the poles and at the equator of about 0.3%, which is small but measurable. And then this component here is our tangential component, which we didn't have when we were not considering the rotating reference system. So if you have free fall, you're actually not in the Earth, you're not moving towards the center of the Earth. You will have a slight tangential component, and you can then look at the ratio of G tangential to the radial component and look at the maximum. So you're looking, here, this is where this goes to a maximum at 45 degrees, and you get that this has its maximum. I have a typo. So so this is the angular the maximum here is going to give you about 0.1 degrees. So there is a very, very, very small deflection due to the tangential component. It is functionally very difficult to measure the difference. So effectively, we often define G as G, whatever G is that we measure. And that is taken as the reference system, but in practice, it won't actually point exactly towards the center of the Earth. We can then return to the Coriolis force, and look at that. That, again, has the form 2mr dot crossed with omega. So this is the same thing as 2mv crossed omega. So this is the velocity in the rotating frame. So this is what you would see in the Earth. We can draw a parallel to the magnetic force. Not actually, it's not a very deep parallel, but it can help you think about what is going on. So you have a velocity crossed with a constant. So here we have a velocity crossed with a constant. So in many ways, the Coriolis force kind of acts like a magnetic field. Um, and we can look at, for instance, the force on a baseball with a velocity of 50 meters per second. Then the maximum acceleration is going to be 2mv omega, or sorry, the max without the m, because we're talking acceleration. The acceleration is 2v omega, which works out to be 0.007 meters per second. So that is very small relative to g, but it's important to note g moves this down, and what happens with the Coriolis effect is that it causes a deflection. So if I am, this is going to be a little tricky for me to work out. So if I am here, this is omega, and I am standing at the equator. So here I've got x, and here I have v cross b. So if I throw a baseball, let me actually, so if I throw a baseball north from the equator, then my omega cross, v cross omega is 0. If I throw a baseball, let me throw it here. So that would be throwing it west. And here I have to use my left hand so you guys see it correctly. Omega cross V, that is going to give an apparent force. Let's see. I think I actually want to not do quite at the equator. So we're going to consider this point. And, yes, the book has a much better way of doing it because the book thought about this longer. And if I am winging it and trying to come up with different perspectives, here, this is looking down on the equator. So omega is out like this. And if you, so now you can look at some velocity like this. We are looking down, so we're looking at the northern hemisphere. So if this is the velocity, v cross omega, if you are, we are looking, I have to do this to have you look at, to have it work out. V cross omega is then like this. V cross omega is then like that. And what we see is that in the northern hemisphere, you generally get a rightward, you get bumped rightward. In the southern hemisphere, you generally, so I think here we're looking at the southern hemisphere because I used the picture from the book and it's all the mirror image. So in the northern hemisphere, you tend to get bumped right or clockwise. And in the southern hemisphere, in the southern hemisphere, you tend to get bumped in the exact opposite way. Yes, northern hemisphere, you get bumped to the right, and northern hemisphere, you get bumped to the left. And so the Coriolis force causes an apparent rotation. And this does not matter for short distances and slow speeds, but it can matter for rockets and long-range missiles. Again, this field was developed to be able to make better weapons, whether we don't have to like it, but that's what this was originally developed for. You also can have a Foucault pendulum, which the real effect is that it is going for a long time, which is that you have a pendulum on the surface of the Earth, and because that is basically just going on, it's rotating back and forth, what you will see is that when it's allowed to rotate freely, the axis of the plane in which the rotations occur slowly rotates around the axis as well. So this Coriolis effect is important for instance, long-range gunners, but it also is important for cyclones. So cyclones are, of course, cyclones and hurricanes, typhoons. So what happens is that you have a region of air with low pressure at the center of the storm, which causes a bunch of air to move inward. And if you only had the region of low pressure and you didn't have the rotation of the Earth, then all the air would move inward, the pressure would equilibrate, and then nothing would happen. But because of the Coriolis effect, it actually, because it has a velocity, it starts to move and it starts to actually rotate. And here I'm going to reiterate the quotable thing that I found in this chapter. Both the Coriolis effect and the centrifugal forces are at root kinematic effects resulting from our insistence on using a rotating frame of reference. We see everything in the frame of the Earth, so we see these apparent forces, but they are not actually real forces. They are simply because we insist on using our own perspective to describe everything. Sometimes it's possible to work in the inertial frame and transform it, but usually it's more complicated, so we opt typically to live with these fictional forces. Then we can do the example 9.2. And this is not an example that has any math, but we're going to look at what happens if you are in this rotating frame. And we're going to consider, instead of the Earth, because that's really complicated, a rotating turntable. You guys are probably all too old to remember actual turntables, so we'll call it a merry-go-round. And you guys are probably also too old to remember a merry-go-round because they removed those from playgrounds, deciding they were dangerous. They were also really fun. So you have three people, A, B, and C. And A kicks this is a frictionless surface, and A kicks a hockey puck. So the system is rotating like this, and A kicks a hockey puck on a frictionless surface towards C. Now, if you have straight towards C, and these are supposed to be on a straight line, so if you have no rotation, A can kick straight towards C. A, B, and C, fish don't know they live in water. A, B, and C don't realize that they're rotating. So what actually happens, what A sees, is that the hockey puck rotates like that. And the hockey puck rotates like that because there is an apparent force. The Coriolis here, I'm going to actually direct you to the picture in the book, because if I do the mirror images, all the signs get messed up. And so you guys actually see the opposite of maybe I can even just draw the mirror image of the picture in the book. So it will do this, because here your Coriolis effect goes like omega cross R, omega cross R cross omega. So here our omega is towards you. I'm looking at the back of the arrow. So we have omega, and then R, that is the centrifugal force. I have written up the wrong force. bear with me. And let me just say, I have taught this class 4 times. If I mess up the sign and I have to think carefully, you're going to have to think carefully too, and that's okay. So our Coriolis force is 2m r dot cross with omega, where this is 2m v cross omega. And then v is in this direction, so I have v cross with the v cross with the omega. I think I need to have omega. Yeah, you guys need, omega needs to go that way. You're looking at omega. So v cross omega, v cross omega. It deflects it that way. So you see a deflection to the left. Now in this case, you happen to be able to analyze the problem as well from the stationary reference frame. So from the stationary reference frame, what you see is that the puck goes straight, but A, B, and C, actually the way that I've drawn this, I think I have to switch this to, A, B, and C are rotating away from the puck. So I shoot the puck straight, they are moving away, and they're the problem, not me. So then we can look into the Coriolis effect and what this does to something which is in free fall. Now, by free fall, we mean that it is experiencing no other real forces than gravity. So we're going to start with our handy-dandy equation. Mr double dot, this is now equal to the net force is just due to gravity. And then we have the Coriolis force, or the centrifugal force and the Coriolis force. We can make, to very good approximation when we're talking about something on the surface of the Earth, we can make an approximation that the position is simply r, the distance to the surface of the Earth at that point. And when we do that, we replace this g naught by g effective. So we get Mr double dot is roughly equal to mg, where it's in g effective. It's not the real gravitational constant, but it is the effective one for that particular point on the Earth, because we're not moving far enough for regular projectiles, for instance, for g to change significantly. Also remember that this was a 0.3% effect, so you're talking about small corrections to a 0.3% effect. And then we have plus m 2m r dot cross capital omega. So to a very good approximation, when we have free fall, this does not depend on the position. It only depends on the derivatives of the position. So that is also saying that we can move our origin. And we're going to do that now. And this is where this becomes very specific to things that are falling on the surface of the Earth. And what we're going to do is, so now we are choosing a specific and useful coordinate system. This is omega. I'm going to try to avoid drawing cross products because the mirror image effect makes this really hard to draw. So there we've got position R. Z is going to be perpendicular to going outward from the Earth. And Y is going to be going up. So Y is to the north. And then we choose X to be east. And the way, so here, X, Y, Z. So X is going to be pointing towards me. So you're going to see the back of the arrow. Let's see, X, Y, Z. No, actually, you're going to be seeing this point of the arrow, not the X. So X is due east, And when we choose that coordinate system, we are going to replace our generic vector r dot by very specifically x dot, y dot, and z dot. And then with this choice of coordinates, where we have moved our origin here, our angular velocity vector, we can move vectors around too. We can move an angular velocity vector around wherever we want. There is no component to the east, so we're always choosing due east, whereas north, there's going to be a component to the north, and there's going to be a component in the z direction. And we are using, again, the co-latitude, so this is theta. So there is a 0 in the x direction, omega sine theta in the y direction, it's that component, and omega cosine theta in the z direction, so that if we are at the equator, everything is in the z direction. Now, we can then look at our ugliest term. Often we start by trying to tackle the ugliest term, r cross omega. We're going to not worry about the factor of 2 just yet. And this is, so here we have no component in the net force in the z direction because, we have only have net force in the z direction, and then we are impacted by this this term, and here when we have a y hat cross y hat, that gives us a 0. We have a, well, let me actually be lazy. I'm trying to finish this recording before my appointment at the studio ends. But you guys can do cross products. So I'm not going to do the cross product out. The way I would do this is to take each component and multiply. Well, you can either do a cross product in general. This gets rather ugly if you want to use the vector notation, or you can consider each of the components, which I think is a little bit easier, but then you have to do it for each of the three components. So you get this, and we can translate that into x double dot equals 2 omega y dot cosine theta minus z dot sine theta. Y double dot equals negative 2 omega x dot cosine theta, and z double dot equals negative g plus 2 omega x dot sine theta. So the point here is that before, when we did not consider the rotation of the Earth, we only had an acceleration due to gravity. Now when we consider the rotation of the Earth, we have this apparent acceleration, and we have chosen to basically define our z coordinate to be that which lines up with the effective gravitational acceleration, plus the difference between the effective gravitational acceleration and the point that we actually look at is relatively small. So, and the true acceleration, gravitational acceleration, is relatively small. So now we have our, now we have these equations. Now this is three sets of coupled differential equations. That's ugly to solve in general. But what we can do is that we can solve it iteratively. So we are going to, as a first step, plug in omega equals 0. because, and I'm going to switch colors because this one hardly shows up, because to a good approximation, omega is very small. So to a good approximation, you can assume that omega equals 0. And you will not be surprised. So when you do that, what you get is x double prime equals 0, which is y double prime, and double dot, and z double dot is negative g. We will, by convention, we will follow the book and choose x equals y equals z, although you could easily add an x naught and a y naught. Why not? And then you get z equals h, whatever the, that's the initial z position minus 1/2 gt squared. So that is what we actually, not only would we expect that, but if we got anything different, we would know that we had an incorrect answer. But now we can take that solution, plug it in here, and we get, so here, this is dependent on z dot, and everything else is 0 because we have this solution to the 0th order equation. X double dot then is equal to 2 omega gt sine theta. Y double dot is equal to 0. Z double dot is equal to negative g. And these have the solution. Z still is h minus 1/2 gt squared. The reason it wasn't impacted is because this solution has no change in x dot. If we did another step, we would get an extra term here. Y equals 0 still. X is 1/3 omega gt cubed sine theta. So what we could do with these results is plug these back into there and solve an extra iteration. If we did that, we're then going to have a y double dot term, and there's now a non-zero x double dot term, and the z double dot term deviates from negative g. And what you see, because all the dependence here is on time, there's no reason you couldn't just keep going and solve to higher order. We're going to stop here, because we can already see an interesting result. So what you see here is that if you do not consider the rotation of the coordinate system, then the object simply falls and it only has a z component. But as soon as you consider the rotation, the fact that the coordinate system is rotating, you get a deflection to the east. And we can plug in numbers, and it turns out, just using the numbers the book did, that if you have an object dropped from 100 meters, it is deflected by 2.2 centimeters. Now you can see why that's not a huge effect, because if you have something dropping from 100 meters, it's pretty likely in most cases that you're going to have some wind or something else deflecting it more. But you do have a measurable effect if, say, the example in the book is that you're dropping it in a mine shaft where there's not a lot of wind. You still can get other effects because you still have the air flowing in the shaft. But this does produce measurable effects. It will produce measurable effects, for instance, when you have long-distance ballistics. But the effect is also relatively small. We can then turn our question to we can then use our equations for a different problem, the Foucault pendulum, which is, I don't know of a practical application. I'm sure there is one. It's a really cool device that demonstrates that you can actually observe these things. So a Foucault pendulum is a pendulum that hangs from an axis where it can swing freely in the x and the y directions. So it has a fixed length. We're going to use the small angle approximation so we don't have to worry about large deviations. And then the net force on this is the tension plus gravity. We're actually going to use the same trick that we did before and lump the centrifugal force into the effective gravity, in with gravity and call it effective gravity. And 2m r dot cross omega. So while the centrifugal force may actually be larger in most cases than the Coriolis effect, because we can't tell, like a fish in water doesn't know it's in water, we can't see the rotation very well, we don't know the difference between gravity and effective gravity, especially when the effect is 0.3%. So here, mr double dot is equal to T plus m g effective plus 2m r cross omega. All right, and we are going to use small angle approximations. And then we have this convoluted drawing. So here's our axis for the pendulum. We have y, and actually we're going to have this be y so that it looks like a right-handed coordinate system to you. This is x. And here our pendulum has a length L. Let me actually, length L. And then there is a tension. I've tried to exaggerate things a little bit in order to be able to draw it. So we have a tension there. And the tension has components in the, here this is, if I project this down, there is this component, and then this is not meant to be, this is meant to be at a slight angle. I am just not really an artist. So there is a y component, and there is an x component to the tension. For small angles, the z component of the tension, it is T cosine beta, which is approximately equal to the total tension, which is equal to mg. And the x component is then negative mgx over L. We're actually not really going to be too concerned with the z components because the object is fixed in z. Or at least the distance is fixed in z. So it's moving a little bit up and down, but that's not the major effect. Ty has the same form. And we're going to use our equations from, well, we can use the same effect, the same result that we had before, except now we are adding a term due to tension. So x double dot, we now have, is equal to gx over L plus 2y dot omega cosine theta. I have then assumed z dot is roughly equal to 0. So my z dot term goes away. Y double dot is then, I'm looking at two equations, so bear with me. Negative gy over L minus 2 x dot omega cosine theta. And we are assuming that z is basically fixed. We are going to define omega naught squared to be g over L. And when I do that, so here I've basically said, I'm not worried about the z components. I'm going to approximate them as 0. And what you can see now is that we've got two coupled second order differential equations. We actually did come across a way to solve this before. So we have y double dot plus omega naught squared y plus 2 omega z x dot equals 0, and then x double dot plus omega naught squared x plus 2, sorry, this one is, the x component has a minus 2 omega z y dot, and omega z is omega cosine theta. So this is the co-latitude. So this is going to depend on position. Now the book goes through re-deriving the solution. It isn't teaching you anything new. It uses it solves both of them by expressing the solution as eta equals x plus I, y equals a e to the negative I theta z t cosine omega naught t. So you can use that as a trial solution. I don't think there's any new educational math in that. So then we can look, so I will simply write down the solution, and I'm going to write it a little bit more general than the book. So y equals some amplitude, initial amplitude, cosine omega z, let me write that legibly, cosine omega z t plus, let me call this capital omega. Now let me come up with delta, and then cosine omega naught t plus gamma, and then x is the same form, but this guy has to be sine omega z t plus delta cosine omega naught t plus gamma. So here you have some initial oscillation, which is just our pendulum moving in a plane without considering a rotating coordinate system. So the omega naught squared is g over L. You have that oscillation, but on top of that you have this, it's the x and the y components are changing. So the Foucault pendulum is rotating as the day goes on. And the angular frequency for the rotation depends on the co-latitude. Now, if you are at a co-latitude of 90 degrees or the equator, then this doesn't happen. Your Foucault pendulum will not rotate. It will just keep going in whatever direction it is going in. And we can look back at our force equations, and that's because you're not getting any deflection in the x or the y direction. But if you are, but as you change your latitude, you can use the, the book uses a latitude of 42 degrees, which is a co-latitude of 48 degrees, and you get that rotation is something around 240 degrees in a day. So that means that it's going to go most of the way around the circle, and you will actually see if you watch it over the day that the angle that the pendulum is rotating at is changing. And I'm going to skip the last section because I didn't really feel like that added much.